Okay, now let's think about fusion as a viable energy source. Um, for a for two or more nuclei to get close enough to fuse, remember there has to be a lot of heat so that the nuclei have enough kinetic energy to get close enough for the strong nuclear force to take hold. So very, very strong, hot conditions are necessary, like millions of Kelvin, um, so that the nuclei are in a state of matter called plasma. So around the temperatures at the surface of the sun, essentially. And you can imagine containing that amount of heat is logistically difficult. So that's why it's not super viable. There are one or two, I believe, fusion power plants in the United States. I visited one a few years ago down in San Diego. It's super duper fascinating. If you get down there, take a look at them and see if you can get a tour. I highly recommend it. All right. So we've talked kind of conceptually about binding energy, right? That there's a certain amount of energy holding a nucleus together, and a certain amount of energy required to put two nucleus together into one, and that's called binding energy. And so when you break a nucleus apart, the parent and daughter nuclei have different masses, and so they release energy. Okay, so this is where our friend E equals mc squared comes into play. After 2 years of taking physics, at least, we finally get to see E equals mc squared, which just relates energy directly to mass with a proportionality constant that's the speed of light squared. Okay, so you can turn mass into energy and energy into mass using this equivalency according to Einstein. So if you break a nucleus apart, the parent and daughter nucleus will have different masses. Okay, so the parent and daughter nucleus will have different masses, and this change in mass between the original and final products of a reaction, this change in mass is released in energy. Right, so literally if there's a decay, or if there's, well, even if there's a nuclear decay, like if there's an alpha decay or beta decay or something, right, you're starting out with a parent nucleus sitting still. When a decay happens, you've got both the parent or both the daughter nucleus and like a alpha particle. Those have some kinetic energy, right? There's energy released, and the amount of energy that's released in that decay is equal to the difference in the mass from the parent nucleus and the daughter and other products. Okay, and so instead of using E equals mc squared, we see how much energy is released is equal to the difference in mass between the parent and daughter and products and times c squared. Okay, and this equation is what would be in your data booklet. And so here, again, release energy. Okay, and this delta M is the difference in mass. And it's also known as a mass defect. All right, and so this is how, like, if we have nuclear reactors, those nuclear reactors are strategically allowing fission or fusion reactions to happen, right? Typically, nuclear reactors are fission reactors, right? They're taking parent nuclei and breaking them apart. And the difference in the mass of the initial and the product after they're broken apart release energy. And that turns into heat. And that energy is released as heat, and that heat goes into heating up water that turns to steam, spins. That steam spins turbines that have magnets in them that rotate, and electromagnetic induction ensues and pushes some electricity into our grid. All right, so here's an example. The most abundant isotope of helium, 4-2, whose nuclear mass is 6.6447 times 10 to the minus 27 kilograms. For this nucleus, find the mass defect and the binding energy. Okay, so if you want to find the mass defect, you want to look at the mass of the nucleus and compare it to the mass of its products. Okay, so let's take a look at this. We've got 2 protons and 2 neutrons. Okay, so this is 2 times the mass of a proton. And 2 times the mass of a neutron, 1.675 times 10 to the minus 27 kilograms. All right, and when you add that together, you get 6.696 times 10 to the minus 27 kilograms. All right, and then what's the difference between that? This is the daughter. And the parent is 6.6447 times 10 to the minus 27, right? If you subtract them, you will get a difference of 0.0513 times 10 to the minus 27 kilograms. Right? A nucleus is made up of 2 protons and 2 neutrons, right? This specific nucleus is. But if you take the masses of the parts, compare them with the mass of the complete nucleus, you get a mass defect, right? A difference in mass. Okay? And that mass defect is associated with some binding energy, right? The energy required to hold those nuclei into those protons and neutrons into the nucleus itself. Okay, so we can find the energy that's released by doing delta m c squared, which is 0.0513 times 10 to the minus 27. And then the speed of light is 3 times 10 to the 8 meters per second. Go ahead and square that. And we get, if we were to break a helium nucleus apart, there would be a release of 4.617. Gee, manitly, I'm writing off the board here. 4.617 times 10 to the minus 12 joules, right? And then if we divide by 1.6 times 10 to the minus 19 joules per electron volt, we would get that this is about 28.3 mega electron volts. Cool. All right, so a couple of classes ago, if we continue talking about binding energy, we determined the atomic mass unit. If you remember, one atomic mass unit was 1.6605 times 10 to the negative 27 kilograms. We want to know what is the binding energy for 1 atomic mass unit. So what is the binding energy for 1 atomic mass unit? Okay, so let's find out. E equals M. 1 atomic mass unit is 1.6605 times 10 to the minus 27 kilograms per atomic mass unit times the speed of light squared. And we end up with energy, binding energy is 1.4924 times 10 to the minus 1 joules. And then convert that to electron volts. And we end up with a binding energy of 931.5 mega electron volts per atomic mass unit. And that's going to be really important because the easiest way to find binding energy is instead of doing E equals mc squared all of the time, we can just say, we can find the mass or the binding energy by taking the mass defect in atomic mass units and multiply it by 931.5 mega electron volts per atomic mass unit. We don't even have to deal with E equals mc squared, and that will be convenient because most of our masses for nuclei or subatomic particles will be in atomic mass units anyway, and this is a direct conversion. Okay, so that's pretty cool. So we could try this example again using atomic mass units. Right, we could do the atomic mass of helium is 4.0026 U. Okay, so two protons. The mass of a neutron is this. The atomic mass. Okay, that's a proton, so 1.0078 plus 2 times 1.0087 will give the mass of the components of a helium, and that's 4.033. Okay, and then we subtract the mass of the, this should be 2 O's, excuse me, 026, so that's the mass of the parent. This is the components, mass of the parent. Subtract, and you get 0.0304 atomic mass units. And if we plug that into our energy equals the mass defect in atomic mass units times 931.5, then we end up with the energy released is 28.3 mega electron volts. Right, this is mega electron volts per atomic mass unit. And this is way easier. Right, there's no conversion. It's just subtracting, plugging it in, and you get your answer in mega electron volts. Easy peasy. All right. So that's the end of this week's lesson. That's the end of nuclear physics. Take a look at the pages I'd like you to refer to, and there are a couple problems if it strikes your fancy. See you guys next week.